So in this video, I will be talking about the reaction mechanisms for ketones and aldehydes. Okay, so to start, the first thing to go over are the carbon nucleotides. So the mechanism for all of them is pretty much the same. So you have your starting ketone, and then you can add an NaCl, an aldehyde, your graveyard, or your organolithium. So your NaCN, you'll end with your alcohol and then your CN. The alkymide one, then you have OH. It's an MGBR. So you should see that there's a pattern here. Oh, and then the Li is also the same as MGBR. Okay, so the mechanism, I'm going to do it with the alkynide ion. So you have your carbon, right? It's negatively charged. So your first step is the nucleophile attack. So then you have your O that's negatively charged and your attached carbon nucleophile. And then it's very simple. The second step is H3O plus, and you want to separate it from the first step because, again, with like the MGBR and the Li reagent, you can't mix those with the water, or that will result in those reacting and the ketone not reacting. Here you have H3O plus, or you can also do it with H2O. Grabs the H, and there you go. That's the carbon nucleophiles. Next, we'll talk about oxygen. So first, I'm going to do the Mr. Standard H3O plus and heat. So this is going to make something called a gem diol. So the way this works, first you have to protonate your carbonyl. So this results in an activated carbonyl, which then gets attacked by water. And then you can use another molecule of water to deprotonate, which results in your gem diol. That's your first type of oxygen nucleophile. Another type is when you have, so I'm going to do it with alcohol, but you can essentially have any RLH. Then you have catalyst and heat. So this is going to make something called an acetyl. And so for this, you're going to have kind of the same as the water mechanism, where you have the carbonyl protonated first, but instead of using an acid, this acid is going to protonate your alcohol reagent. So the thing you're protonating with is a protonated form of your alcohol. This activates the carbonyl. and then the carbonyl is attacked by your alcohol. Then it's also deprotonated by the alcohol, which then causes you to reach O, and these reactions are all reversible, except for the carbon nucleophile. So even here, you can go backwards. The carbon nucleophile you can't because you're adding carbons, which can't be expelled. But here you can't go backwards. So then you're going to get to something called a hemiacetal. So from there, this alcohol gets protonated. And then because it's a protonated alcohol, it's a good leaving group, so it leaves. This comes down, which is very similar to your protonated carbonyl. So now this is activated, so it can be attacked by another alcohol molecule. I go this way. And this leads to your final product once it is deprotonated. Okay, so there you have it for that mechanism. There is one more thing that's important. Oils, you can have something called a cyclic acetyl. And this is important in synthesis because it's a good protecting group. It won't react under extreme basic conditions or mildly acidic, and it stays during reduction and oxidation mechanisms. The mechanism is going to be the exact same thing. We're first going to protonate this, then protonated the carbonyl. Okay, got ahead of myself there. And then this is going to attack and deprotonase. And this is your hemiacetal. So then protonated form of the alcohol is going to protonate here. So the water leaves, this comes down. And then since there's another alcohol within that same molecule, it'll come in here. That will be deprotonated. Okay. Same thing, just for molecular. Okay. Now let's do nitrogen nucleotides. So the first thing you can have is primary amine. And your primary amine is going to make something called an imine. So this mechanism, again, you're going to use this catalyst here to protonate the amine. So you'll have iPad. You have the protonated form of the amine, which will protonate the carbonyl. So this is in pH 5 conditions, which is like a buffer, mildly acidic. Will activate your carbonyl and then be attacked by the nitrogen. This is also and that same amine will deprotonate. Which will then, the protonated form will protonate this oxygen similar to the O nucleophiles. So this will come down, causing this will also leave since it's a good leaving group. And the final step is to deprotonate. Something in your image. And then the other type of nutrient is your secondary image. And this will result in the formation of an enamine. So it's very similar to the imine mechanism. You're going to have the protonated form. And again, this protonated form comes because of this catalyst, which is protonating the amine. is then attached by nucleophile. Then deprotonates. Then you'll have protonated form. Protonate the alcohol. Then this will come down, this will leave. So the only difference in this mechanism is you don't have a hydrogen to deprotonate. So instead, the base will pull off a hydrogen here. So this is your only different step. So you have R2NH. Pulls off this proton. This will fold down. This will go up, which will result, sorry for the long arrows there, in your enemy. Okay, so the only thing worth noting is if you have, instead of page 5, if it's page 6 to 9, your first step is protonating your alcohol first, like here, the alcohol is protonated to come here. Instead of that, you're just going to directly attack, because this is a mildly basic condition. So you can still have, you're still going to have your catalyst because it's mildly basic, you can still have the plus charge. And here you can't just transfer the positive charge from the nitrogen to the oxygen. You can do it intramolecularly. So you first have to deprotonate. And use your protonated amine. Protonate the oxygen. And then you'll get to that same intermediate. So here you could protonate first and then deprotonate instead of doing it the way I did where I deprotonated the amine and then protonated the oxygen. And the rest of your steps are the same because you get to this exact intermediate here. This is called a I think it's a carbonylamine. Might have spelled that wrong. Okay. So now Now we will do hydrogen. So this is where you have LiH4 and NBH4. This will reduce it to alcohol. So this ally is going to interact with this carbon, which activates it. So then you'll have a hydrogen here attack. You'll have another touched oxygen, and then the hydrogen around. Ally is still floating around. Now you have the LH3. So now this oxygen here is going to act up aluminum. Forming a complex here. Still have Li floating around. And now this Li, this ALH3 now, that's interacting with this oxygen, can attack another one of the carbonyls, which is interacting with a different Li. And now you have negatively charged. Then you have your Al. Now there's two hydrogens, and then here it's still interacting with that other one. So now the second one, this one here, is this. So this is going to attack the Li. Now you'll have this. Sorry, ran out of a little room there. So then this will do the same thing that's happening here. So eventually you're going to have you do the same thing. You'll have a complex of 4. And then the second step is your first step is this. Second step is to add H2O or H3O plus, and you'll get this product. So you'll actually get 4 of that product. Okay. And then this also works with aldehydes, which will make primary alcohols. Okay. So LiALH4 and NADH4 are reducing agents. So reducing from so now I'm going to talk about some other reducing agents. So you have your imine that you made previously. This is your imine, right? If you use NADH, you can reduce that to an amine. So this only reduces amines. It's selective. But you could also use NADH4. But if you use NADH4, you have to make sure there's no other ketone. Because if you use it, you have something like this. When you use NADH4, you'll reduce this, but you'll also have reduced your ketone to a secondary alcohol. So this is a case where you could use that protecting group that we talked about earlier, because this can withstand reducing agents. And then use NADH4. If you want to preserve, instead of this, you'll have your ketone stay. Well, from other reducing agents, you have your H2 catalyst. This will reduce, but it will not reduce your ketone. You also have your benzene. This will reduce it to a cyclohexane, and your alcohol, your aldehyde or ketone will become an alcohol. So in this case, because it's an aldehyde, it will become a primary alcohol. But if it was a ketone, it would be a secondary alcohol. So this will pretty much reduce everything. And then say you have a ring with ketone, you have an NO2 group. Your LiAlH4 is a strong reducing agent. So, and then say you have also an ester over here. So the LiAlH4 will reduce your ketone and your ester, and the NO2 will become an NH2. If it was NADH4, which is a bit milder, your NADH4 will not reduce the ester. It will reduce your ketone. So it reduces ketones and aldehydes, and it will not reduce your NO2. So LiAlH4 is strong, NADH4 is mild. And so this ester, LiAlH4, can also reduce other carboxylic acid derivatives. So it can reduce, if this was instead of MME or carboxylic acid. Okay. So I'm going to give you guys one example. Okay, so see if you can figure out what this would become if you used LiAlH4, NABH4, your H2 and metal catalyst, or your H2 and high pressure, high heat. Okay. So let's go to oxidizing agents. So these don't have to do with the mechanism, but just to know a bit of them quickly. So cyclohexane turns an ketone into an alcohol. Oxidizing will make an aldehyde. So say you have benzene with a primary alcohol coming off and secondary alcohol. So your first reagent, you can have PCC or Swern oxidation. And this is mild. So this will reduce your primary alcohol into an aldehyde. Your secondary alcohol will be a ketone. If you have Jones or KMNO4, this is a strong oxidizing agent. So your primary alcohol will become a carboxylic acid. The secondary alcohol will also be a ketone. There's only one hydrogen. And then lastly, you have other mild oxidizing agents. So these are more mild than PCC and Swern. So this will not reduce your primary alcohol. So not reduce primary alcohols. But it will reduce your secondary. Or not reduce, sorry, oxidize. Sorry, that's not my bad. So it'll oxidize your secondary. So it'll oxidize secondary, but not primary. Oh wait, shoot. My bad. It'll only reduce an aldehyde. So okay, so say you have not reduce your primary alcohol, but your aldehyde will become a carboxylic acid. So it will only oxidize an alcohol. Or not an alcohol, sorry, an aldehyde. Sorry about that, guys. Okay. And your last oxidation is the oxidation. You do not have to know the mechanism of either. Which will essentially cleave this bond, kind of like ozonolysis. And it'll form aldehydes. And then to make this, use OSO4. Okay. So the next thing is reduction. We have ketone. And there's 3 ways to reach methylene. So it essentially will reduce, it'll replace this group with 2 hydrogens to become an alkane. So your first method is in basic conditions. You first form an imine. So this is extremely basic condition. So the mechanism of it will look slightly different than the imine formation using pH 5 or pH 6 because you cannot have positive charges in this extremely basic condition. So we'll go over the mechanism next. And then you have super acidic. So you don't need to know the mechanism for this one. But it's NH2 concentrated HCl. So this is an enzyme reduction. First one, your basic one, is Wolff-Kishner. And then the third way, similar to the cyclic acetyl we did, instead you're using thioacetyl, which is sulfur. You use mild acid, H3O+, and the second step is using nickel. So this is mildly acidic. So depending on the conditions you have, you want to, and the groups in a molecule you want to keep, you have to determine which one to use. First, let's go over the mechanism. Your Wolff-Kishner first. So it's going to do and then since you don't have a positive solution, so the KOH is going to immediately come in and put that positive charge. And the water, since the KOH is coordinated, this. Oops. Sorry about that. Okay. So now you have this intermediate. Actually, I'm going to do this in 2 pages. So this will first form a hydrazine, which is a type of imine. Just so it'll be cleaner. Okay, so now, because the conditions are extremely basic, instead of protonating the alcohol, the OH is going to take a proton from the nitrogen This only happens in extremely basic conditions. And you have a negative charge here, which is really strong, so this is going to come down and push the OH off, which won't happen in regular conditions because OH is a bad leaving group, but because it's highly basic, it'll do that, and it'll form your hydrazine. Okay, so then this is just a continuous thing. Then your hydrazine. Okay, let me actually draw it up. You're going to have your KOH come in. I'm going to pull off a proton here. This is negative charge. So the charge will come down here. This one from a negative charge on orbit. So now this will pull a proton from the H2O. Now you have that H3. And the next step, very similar to the beginning, it'll take off this proton. Negative charge. So this will come down. So put a negative charge on the carbon. So now you have liberated N2 gas. So this is essentially your triple bonded N2. Now you have a negative charge on this carbon. And then again, so we'll pull a proton from H2O, which will form your short long arrows. So this, you have your two hydrogens. Okay. And then the only other one to know the mechanism of is probably the first step of your biodigester. This is going to be very similar to Cynthia's, or the so you have this protonated. This will attack. Your protein. Now this will be protonated by your protonated form of the nucleophile. And this will come down, this will leave. Now you'll have this come in and attack. She'll deprotonate. Now you'll have your deocetyl. Then your second step, you don't need to know the mechanism of. Just any nickel. And we'll make it reduced. Again, the 2 H's are here. Okay. So then, just quickly to talk about when you would use them. Let's say you have a molecule like this. Oops. Just draw that nicer. You have a molecule like this. And you want to get something like that, where the amine group stays, but your ketone is reduced. So this amine could also be, again, your carboxylic acid, ester, or could be an acid component. So if this is the type of reduction you want to get, this will not work with clemenson or with Fischer, because in extremely acidic conditions, this amine group right here will also be reduced. And in extremely basic conditions, it'll also be reacted. You won't be able to protect it. Now in this case, the only thing you can do is okay. Let's say you had something like this. So in this case, you can't use your thioacetyl. That won't work because the Raney nickel will reduce this alkene to an alkane. And so you're left with clemenson or Wolff-Kishner. Your Wolff-Kishner is basic, your clemenson is acidic. So if you think about it, clemenson has HCl in it, right? It's extremely acidic. That will also hydrogenate this alkene because you'll get your Cl attached, right? So clemenson also will not work. So the only one you can use in this case is Wolff-Kishner. So you just have to remember the other parts of the molecule and see which conditions work best. Okay. The next over is chemical. I think I spelled that wrong. Oh no. Arrangement of deals. This will okay. So you can either have symmetric or you can have asymmetric. So when you're asymmetric, your carbocation will be at more substituted position. Okay, for the mechanism, you're going to have your H2SO4 protonate to alcohol. Will then leave, forming a carbocation. Oops. Then you will have, in this example, you'll have a hydride shift. So remember, we first look for a hydride shift, and then if there's no hydride, it would be a methyl shift. Then this will come down. Then you'll have, this is also reversible, I believe. This. And then in this case, you'll have HSO4 minus. That'll deprotonate, forming your ketone. And then down here, so you have a primary position and a secondary position. So you're going to protonate. I'm just going to read it as H plus, but it's SO4. Protonate is a then leave. We'll have a hydride shift, so it'll come down. So then be deprotonated. Forming an aldehyde. So then the last thing to go over is the leading reaction. So this will turn your carbonyl into a carbon-carbon double bond. The first thing is going to be the formation of your reagent. So you'll have your PR. So this is going to be the first one. Which will result in positive charge here. And on your second step, you'll have strong base, so KOTBU or NaH. Here I'll use KOTBU. This will pull off a hydrogen, forming a negative charge there. So this is called a phosphorium halide. So that is going to be your reagent. Will form a carbon-carbon double bond. And here, since you have an ethyl, we'll have an ethyl. Your byproduct is H3. Okay, so what did this happen? Here, this oxygen is going to affect this phosphorus. This four-member group here So then, now what happens is bond between the phosphor and the carbon comes down, and then the bond between the carbon and oxygen will come up, which will cause you to have the product. So one thing to remember is to this is where not says you'll have your consistency. So as an example, if you have the here, or hold on, this sort of related. So this unit is not resonance. So this will have, you can either have it where you have the methyl group on one side, and H on the other, right? Like this, or the two H's can be on opposite sides. So this would be your cis, since the two priority groups are on the same side, here and here. This would be your trans, your E, since the two priority groups are on opposite sides. So what I'm saying is when you have a reactive lead, this is your major product. If you have a stabilized lead, you'll only get the trans product. So if you have you see how in this lead you can resonance stabilize it? Oh, hold on. It's resonance stabilized. So in this case, the only product you can get so I like to think of it as this carbon here is always going to be your first carbon. So then you have 1, 2. And in this case, see the two groups are trans. Okay. And then the last thing, you can also have a sulfur oxide. So the first step is formation. Very similar. This will and you have, I'll use NaH this time. There you have a sulfur unit. And then So first thing is the cell attack. So again, if you get confused with the carbons, this here is attaching directly to where the ketone is. Then you have one extra. This example. So then in this case, instead of attaching to the sulfur, just a positively charged, this is a good leaving group. So the oxygen will negatively charged will attack, and this will leave, resulting in epoxide. And your byproduct is same thing you started with. Okay. So I'm going to provide you guys with examples to work through on the next few pages. It's just going to be mechanisms you can practice, and there are no particular orders that could be from anything else in this video. Thanks for watching, guys.